We need to develop a method for solving systems that doesn't require us to visualize things. Because as soon as we get past 2 equations and 2 unknowns, or even 3 equations and 3 unknowns, or 4 equations and 4 unknowns, the visualization either becomes too difficult because we're trying to imagine where 2 planes are, and it's going to be really hard to decide where they intersect based on visualization. Or if we have 4 equations and 4 unknowns, now we have 3-dimensional objects in 4-dimensional space, and we really just can't picture what's going on and visualize things. So we need to break this down into pieces. Here's what we're going to do. I'm going to take this system and I'm going to encode it into an augmented matrix. I'm just going to write down the augmented matrix and see if we can figure out how I did such a thing. So first of all, I need to write a matrix. Around here, we're going to put our matrices in square brackets. The first row of this matrix will be 1, -1, 1. The second row of this matrix will be 3, 2, 8. So it should be pretty easy to see how I wrote this augmented matrix. Each row represents an equation, and we just have to agree that we're going to put our variables in a particular order. In this case, the variables went in the order. Here's a column for the x's, here's a column for the y's, and here's a column for the constants. And each row represents an equation. Each column corresponds to a variable. So each column will correspond to a variable or the constant, and each row represents an equation. So we have a column for the x's, a column for the y's, and this column here is for the constants. So since we have a column for the constants in our system, this is the augmented matrix of a linear system. Sometimes I want to make sure that I separate out. I remind myself that this is an augmented matrix. This column for the constants is what makes this an augmented matrix. A column for the constants means this is an augmented matrix. Since we're new to this, we want to remind ourselves when we're dealing with an augmented matrix or just a matrix. So let's put a dotted line. Oh, this is not dotted, this is a dashed line. Put a dashed line where the coefficient matrix ends and the constant matrix begins. So a dashed line is a good reminder that we're dealing with an augmented matrix. It's not necessary, but we're new, so we're going to practice reminding ourselves that this is a special kind of matrix called an augmented matrix of a linear system.
I have a question.
Yes.
So how we can draw a dashed line when we write it in Canvas?
In Canvas, I have not figured out how to make the dashed line. So this is going to be a handwritten thing. So in Canvas, we're just going to have to know that when we're looking at an augmented matrix versus not an augmented matrix. Okay. Usually at the beginning, if I give you a matrix, I'll say, this is the augmented matrix of a linear system, or I'll just say, consider the matrix A, in which case it's not an augmented matrix.
Thank you.
Here's what we're going to do. Let's think back to how we can solve this equation. if I want to solve this equation, one of the methods we have, if we set your Wayback Machine to elementary algebra again, I can multiply one of the equations by a constant and add the equations together. So what we're going to do is we're going to multiply this first equation by -3 and add it to the second equation to produce a new equation. So let's multiply the first equation by 3 and add it to the second equation. We know that this is a perfectly legal move algebraically. It will not change the solution set. So I'm going to multiply the first equation by 3. That'll give us 3x minus 3y is equal to 3. And I'm going to add that to the second equation, which is still 3x. I said -3, right? Multiply the equation by -3. Now it should be clear why I'm doing this. And I'm going to add it to the second equation. So the reason I multiplied by -3 once I fixed it is that -3x plus 3x is 0x. 3y plus 2y is 5y. -3 plus 8 is 5. I can do this and not change the solution set. Now I have an equation that will tell me what y is equal to. Now if I multiply by 1/5, I can find out that y is equal to 1. So if 5y is equal to 5, if I divide everything by 5, multiply by 1/5, I find out that y is equal to 1. So this equation is equivalent to y equals 1. Now let's take a look at what our system looks like. So our system now we have our original equation, x minus y. I'm doing this because we're not trying to actually solve the system, we're trying to develop a method. So our equation x minus y is equal to 1. Our new second equation is y is equal to 1. Well, if y is equal to 1, I can plug that into the first equation and find out that x must be equal to 2. That's if our goal is to solve the system. But solving the system is not our goal. Developing a method is. So let's take a look at this new system and think in terms of the augmented matrix, what we did. The first thing we did was we took the first equation and multiplied by -3 and then added it to the second equation, and that became our new second equation. So if we start with this, I didn't give myself enough space. You know, if you had a professional teacher, they would have planned for this and left space to write the stuff here. But y'all are stuck with me, so you're going to have amateur moves like this. So what I'm going to do is I'm going to look at this augmented matrix and know that it represents a system of equations. I'm going to remind myself, this is an augmented matrix of a system. Each row corresponds to an equation. So what I did was I multiplied the first equation by -3 and added it to the second equation. Let's write down in code what that means. I took -3 times the first row and added it to the second row, and that became my new second row. Now, the reason that we would want to do something like this, because it seems crazy on such a small example, especially when we already know what the solution is. If I do -3 times the first row plus the second row, -3 and 3 is 0. 3 and 2 is 5. -3 and 8 is 5. I'm just keeping track of what happened in the equations, and I don't have to write all the x's and y's and equal signs. Then I just did 1/5 of row 2 and made that my new row 2. So the augmented matrix is 1, -1, 1, 0, 1, 1. And this third equation, this second row corresponds to the equation y equals 1. 0x plus 1y is equal to 1. So this system corresponds to this augmented matrix. Whatever we did to the equations, we can do to the rows. And we'll have an augmented matrix for the equivalent system. Now, as I said previously, if our goal was just to solve the system, if we have little tiny goals like that, then if y is equal to 1, we can see that x is equal to 2. And if the goal is to solve the system, it's like, oh, dude, we knew that already. And like I said, it's not about the solution, it's about the method that we're trying to put together. So let's do the same thing again. Let's use this 0, 1, 1 and use it to eliminate the y from the first equation. So I'm going to take row 2 and add it to row 1. So I'm just going to take, now I'm going to write this next to row 1. I'm going to take row 2 and add it to row 1, and that'll become my new row 1. So 0 and 1 is 1. Um, 0 and 1 is 1. 1 minus 1 is 0. And 1 plus 1 is 2. Now, this augmented matrix corresponds to x equals 2 and y equals 1. And that's what we want. So this corresponds to x equals 2 and y equals 1. Performing row operations is performing equation operations. It's just combining the equations to eliminate variables so that we can get down to a solution set. Row operations are equation operations. Row operations are equation operations. Questions? All right. So this is going to be the basis for our method. What we want to be able to do is take our linear system, encode it into an augmented matrix and perform row operations until we get to a form that we could read as the solution. The way that I know which I'm replacing with is I write it, my particular method is to, I'm going to replace row 2. Sorry, in row 2, I write what I'm going to do. -3 row 1 plus row 2, and that's going to be my new row 2. Sometimes I'll write, since we don't have lines on the paper, this is my new row 2. Then I can say 1/5 of row 2 is going to be my new row 2. Then in this third step, I did row 2 plus row 1, and that became my new row 1. So you could say, put an arrow and say this is going to be the new row, or I usually just write it next to the row that's getting replaced. So, as usual, we want to look at all the things that could happen. Here we have a consistent system with exactly one solution. Let's do this row operation business on the other examples that we had. So let's take a look at x minus y equals 1. And it was minus x plus y equals 1. We're going to do the same thing. We're going to write the augmented matrix of the linear system, and then we're going to perform row operations to get this down to something we can read as a solution set. Now, we know that there are no solutions, so we should expect some shenanigans to show up when we're doing these operations. So let's first write down the augmented matrix. The X column is 1, -1. The Y column is -1, 1. And the constant column is 1, 1. I'm going to start in the upper left corner, and I'm going to use that 1 to zero out the rest of the column. So I'm going to highlight this first one. I'm going to use this 1 to zero out the rest of the column. I'm going to use that 1 to zero out the column. So what I'm going to do is take row 1 plus row 2, and that will be my new row 2. So I'm going to do row 1 and add it to row 2, and that'll be my new row 2. The first row I'm not changing. So I'm going to keep that 1, -1, 1. After doing this operation, 1 minus 1 is 0. -1 plus 1 is 0. And 1 plus 1 is 2. And so at this point, we need to stop and look at that second row. At this point, we see that the second row corresponds to 0x plus 0y equals 2, and that can't happen. So this second row corresponds, the second row means 0x plus 0y is equal to 2, which has no solutions. So at this point, we can stop. No more operations necessary. We know that the solution set is empty. No solutions, the system is inconsistent. So when we're reading the augmented matrix, we haven't talked about pivots yet, but if there's a pivot in the rightmost column of an augmented matrix, then the corresponding linear system is inconsistent. We don't want to say that the matrix is inconsistent. That doesn't make any sense at all. Even though technically I know what you're talking about. I got to pretend like I don't so that we use the right words. So this augmented matrix is telling us that 0 has to equal 2 for this system to be consistent, and that can't happen, so the system is inconsistent. The system has no solutions. Any questions?
I have one.
Yes.
So do we always use row 2 to find the solution, or can we use row 1 as well?
We can use whatever we want, but we're going to try to develop a method that we're always going to apply.
Mm-hmm.
Secretly, this
Oh,
is
okay.
going to be the method. But
Oh, okay.
We always want to start in the upper left corner and then kind of march right and down. So we're going to start up here and move this way and this way. It's kind of small to start with, but we'll expand this in the third part.
Thank you.
Let's look. So here's some shenanigans that happened. My coefficients zeroed out, but I still had a number over here. And so this means an inconsistent system. This can't happen. Let's look at our other example and see what kind of shenanigans we get up to there. Because in the third example, we had infinitely many solutions. So let's write down that system, where we still have x minus y is equal to 1. And then this one, minus x plus y, is equal to -1. Let's make our augmented matrix. Our x column will be 1, -1. Our y column is -1, 1, and we can already see the stuff that's going to happen. And now we can see more what's going to happen. I'm going to apply the same thinking. We could, like the question, like was stated in the question, we could start anywhere we want, but let's be consistent, not this consistent, let's be consistent in how we apply the method. I'm going to start in the upper left corner. I'm going to use this one to get zeros below it. So I'm going to do row 1 plus row 2, just like I did before, but different stuff is going to happen. My first row is not changing because I'm operating on the second row. So the first row stays 1, -1, 1. But my new second row is going to be 1 minus 1, which is 0. -1 and 1 is 0. And in this case, 1 minus 1 is also 0. So we can see that the second equation is not adding anything. This is telling us the second equation was the same as the first equation. The second equation is not adding new information. The second row now means 0x plus 0y equals 0. So the second row did not add any information. In this case, the second row is just essentially a copy of the first row. Now, in this case, it means there are infinitely many solutions. In this case, all that's left is the equation x minus y is equal to 1, and that's a description of the solution set. We're not saying infinitely many solutions because there's a row of zeros. A row of zeros on its own means nothing. I'm going to say that again. A row of zeros on its own means nothing. If you're going to write a justification for me in this class and you're saying because a row of zeros, stop. Row of zeros means nothing as far as the solution set goes. But the only equation that we're left with is the first corresponds to the first row, which is x minus y is equal to 1. And that's why we have infinitely many solutions. Note, a row of zeros does not tell us anything about the solution set. For the system, it just means that we had some extra equations that we don't need. But that contributes nothing to the solution set. It just means we had an equation that we didn't need. Questions? Let's pause the video here and look at one more example where we can expand on this method, where we can codify what we want to do in this method. The question says, is there infinitely many solutions because the system is only described by one? That is correct. The system of equations is only described by one of the equations. That second equation was not necessary. That's why we have infinitely many solutions. All right, let's pause the video and look at expanding this to a proper process.